We also have a couple rules of our exponents that involve our quotients. Whether I have a quotient that's overall to a power, or whether I have a quotient of two exponential expressions that have the same base. So let's look at if we have a quotient that's overall to a power. Let's say we have 5 over x all raised to the third power. Well, if we write this without exponents, it'll be 5 over x times 5 over x times 5 over x. Now when I'm multiplying fractions, remember we multiply straight across the numerator and straight across the denominator. So 5 times 5 times 5 is, well, 5 times 5 is 25, times 5 is 125. And in the denominator, x times x gives me x to the third. And notice we could have gotten there with our rule by saying, well, if I have a quotient raised overall to a power, the numerator gets the power, so I'd have 5 to the third, over the denominator gets the power, x to the third. And then we just simplified our 5 to the third to be the 125. What if we have a quotient of exponential expressions, as another example, where the exponential expressions have the same base? So for example, if we have a to the fifth over a to the second. Again, let's expand it without exponents, simplify it like we know our rules of simplification allow us to, and then see if there is the justification for the rule. So a to the fifth is a times a times a times a times a. In the denominator, a to the second is a times a. Well, when I have a fraction and I have it all attached by multiplication in the numerator and in the denominator, we can remove any common factor pairs that we have between the numerator and the denominator. So I have a common factor pair of a's that I can remove for the first part, and then another common factor pair of a's that I can remove. And when we remove those, a quotient of a number divided by itself, as long as I'm not dividing by 0, gives me the value of 1. So I have 1 times a times a, which would just give me a to the third. So when we have a quotient, a division of exponential expressions that have the same base, we keep the base and we subtract the exponents. 5 subtract 2 gives me an exponent of 3 in my simplification. Now that in general is our rule, but it also extends to a lot of the other rules that we have at the end of this list because of what happens when we work with quotients. Let's say, for example, that I have a quotient of exponential expressions with the same base, but their exponents are also the same. So for b not equal to 0, what if we have b to the fifth over b to the fifth? Well, I know that if I'm dividing a number by itself, as long as I'm not dividing by 0, which I'm not, that a non-zero number divided by itself is worth 1. So I know that's what my simplification should give me. It should give me the value of 1. But I also know that I just learned these rules about exponential expressions, where it says if I'm dividing exponential expressions that have the same base, I keep the base and I subtract the exponents. Well, 5 subtract 5 gives me a new exponent of 0. Now, when we're simplifying, we're supposed to write the expression in the most understandable form that we can. And b to the 0 is a valid value for this, but it's not the most understandable form that I can write it, because a much larger percentage of the population understands the value of 1 more than they understand what it means when we say b to the 0. So when we have our base, our exponential expression of our base to a 0 power, that means the number 1. So even if I had 7 to the 0 power, that's 1. If I have in parentheses negative 3, and outside the parentheses to the 0 power, that's 1. We have to be careful, however, on what the exponent is acting on. If I have the opposite of 8 to the 0. Remember, the exponent only reaches what's directly in front of it unless it has help from parentheses. So 8 to the 0 gives me my value of 1, but then I apply the opposite of that at the ending part of the process. So I get the opposite of 1, or -1, for that simplification.